Okay, in this video we are going to discuss on electronegativity, electronegativity, electronegativity of elements. Okay, it is denoted as chi. So, electronegativity of an element is a tendency of an atom of that element to attract a shared pair of electrons towards its side. Okay, for example, you have some molecule A, B, and between A and B there is a shared pair of electron. And if you want to talk about the electronegativity of A, we want to see how much electron density between A and B is being pulled by A towards its side. Or what is the tendency of A to attract the shared pair of electrons towards its side? Okay, that is what we have to measure in order to specify the electronegativity of A. Okay, എങ്കിൽ ഇലക്ട്രോനെഗറ്റിവിറ്റി ഓഫ് ബി ആണ് പറയേണ്ടതുണ്ടെങ്കിൽ ഈ ഷെയർഡ് പെയർ ഓഫ് ഇലക്ട്രോണിനെ ബി എന്തുമാത്രം അതിന്റെ സൈഡിലേക്ക് പിടിച്ചെടുപ്പിക്കാനുള്ള ടെൻഡൻസി ബിക്കുണ്ട് എന്നുള്ളതാണ് ബിയുടെ ഇലക്ട്രോനെഗറ്റിവിറ്റി പറയുന്നത്. So electronegativity of an atom is the tendency of an atom to attract the shared pair of electron towards its side. Okay, that is a general definition. And there are slightly different definitions put forward by different scientists, and we are going to discuss on such approaches by different scientists. Okay, so let us deal with the Pauling's approach first. Pauling's approach. Pauling's approach on electronegativity. So according to Pauling, electronegativity of an atom is the power of that atom in a molecule to attract the electrons to itself. What is that? Electronegativity is the power of the atom. Power of an atom to attract. Where is that atom? The atom in the molecule. Power of an atom in a molecule to attract the electrons to itself. To attract the electrons to itself. Okay, that is called electronegativity by Pauling's definition. Power of an atom in a molecule to attract the electrons to itself. Okay, now Pauling used some thermodynamic data in order to calculate the electronegativities of different elements. Okay, for example, let us calculate a reaction AA. AA means the molecule A2. Okay, this is a homonuclear diatomic molecule of the element A. By saying homonuclear diatomic molecule, we mean that that molecule is formed by the atoms of the same element. Okay, so this is a homonuclear diatomic molecule. So this AA react with another homonuclear diatomic molecule, that is BB, in order to give 2 moles of AB. Okay, or in other way we can write it like half AA react with half BB to give 1 mole of AB. Okay, so in this reaction a new molecule is formed. That new molecule is formed between the atoms of different elements, that is A and B. Okay, and now what Pauling did is that Pauling considered the bond energies or bond dissociation energies of the different molecules involved here. The molecules involved here are AA, BB, and AB. Okay, so the bond dissociation energies, bond dissociation energies Bond dissociation energies of AA, BB, and AB are considered. Here you have to remember that this bond dissociation energy is in kilocalorie per mole. kilocalorie per mole. Okay, that is very important. Okay, keep it in mind, kilocalorie per mole. So bond dissociation energies of different molecules involved here are considered. So the bond dissociation energy of AA is considered, the bond dissociation energy of BB is considered, and the bond dissociation energy of AB is considered. Okay, let us call the bond dissociation energy of AA as EAA, and the bond dissociation energy of BB, let us call this as EBB, and the bond dissociation energy of AB is EAB. By the way, what is bond dissociation energy? That is a minimum energy required to break the bond between these two atoms. Okay, here AA, the bond dissociation energy of AA mean or EAA means the minimum energy required to break the bond between A and A, so that they are separated into their free elements or free atoms. Okay, so here also the bond dissociation, the minimum energy required to break this bond, here also minimum energy required to break this bond. Okay, that is bond dissociation energy. So if you are considering the bond dissociation energies of AA, BB and AB, which one do you think that which one will be greater, which bond dissociation energy will be greater if you think about all these things? Okay, obviously we can think that the bond dissociation energy of AB is greater than the average of the bond dissociation energies of AA and BB, because AA and BB react to give AB. So when a reaction happens, some energy should be saved, or reaction always happen to get a more stable molecule, right? So AB is expected to be more stable than A and BB. Okay, so what is meant by more stable? It is more stable in the sense that it will be more difficult to break the bond between A and B compared to the bond breaking energies of AA and BB, right? So more energy would be required to break a bond between A and B than the average energy for the breaking of AA and BB together. Okay, that is what we can guess from here. So EAB will be greater than the average of EAA plus EAA and EBB. Okay, average. So this is a very obvious result. So here the arithmetic mean of bond dissociation energies of AA and BB is taken. This is the arithmetic mean, right? Arithmetic mean of bond dissociation energies of AA and BB are taken into consideration. Okay. So if you are taking the difference between these two, okay, difference between EAB and the arithmetic mean of EEA and the EBB, and then we can get some value, let that value be equal to delta. Therefore delta is equal to EAB minus EAA plus EBB, okay, EBB divided by 2. Okay, and this quantity is delta. So keep it in mind about this delta. This is very important, and we are going to use this in the upcoming equations. And Pauling put forward a relation between delta, relation between delta. Okay, delta is already defined, and then electronegativity of A, let us call this as chi A, and electronegativity of B. Okay, there is a relation between these three. Okay, because A and B are the elements involved here. Okay, so the relation between delta and chi A and chi B is that delta is equal to 23 into chi A minus chi B the whole square. Okay, that is a relation. Actually, this relation doesn't have so much of the theoretical support. This is an empirical relation. This is an empirical relation. Okay, empirical relation. So, what does it mean? This relation is here based on the observation. Okay, so delta is equal to 23 into chi a minus chi b the whole square, and it means that chi a minus chi b the whole square is equal to 1 divided by 23 into delta, or chi a minus chi b is equal to root of 1 divided by 23 into root of delta. Okay, that is chi a minus chi b is equal to root of 1 divided by 23 is 0.208 into root delta. Okay, so now we have a relation chi a minus chi b is equal to 0.208 root delta, where delta is already defined. What is delta? Delta is equal to EAB minus EAA plus EBB divided by 2, and keep it in mind that all these bond dissociation energies are stated in kilocalorie per mole. So if some problem is asked to you in the examination, and if you want to use this equation, you have to make sure that the bond dissociation energies that you are substituting in your reaction should be in kilocalorie per mole. Then only this equation will be valid. Okay, if you are substituting the values in kilojoules per mole, then you cannot use this equation. Okay, so if it is given in some other units, you have to convert that to kilocalorie per mole. Okay, so that is very important. So we have a relation chi a minus chi b is equal to 0.208 into root of delta. Let me make it in a box. Chi a minus chi b is equal to 0.208 the root delta. Okay, and now later on, Pauling considered the geometrical mean of the dissociation energies instead of the arithmetic mean. So this relation is obtained by considering the arithmetic mean of the bond dissociation energies of AA and BB. Okay. Later on, Pauling understood that if we are taking the geometrical mean, then this relation will be better, or this equation can be improved. Okay, so Pauling considered the geometrical mean. What is the geometrical mean of the bond dissociation energy? Geometrical mean of the bond dissociation energy is root of EAA into EBB. That is the geometrical mean of the bond dissociation. Okay, so this geometrical mean was involved in the relation. So our new delta, okay, let me call this as delta dash, because we are not going to use the arithmetic mean but the geometrical mean. So delta dash is equal to EAB minus root of EAA into EBB. Okay, so that is delta dash. And from this delta dash, again Pauling reached another empirical relation. That empirical relation is delta dash is equal to 30 into chi a minus chi b the whole square. So what is the difference here? Here it is 30 instead of 23. Instead of 23, what we used here. See, here we used 23 when we considered the arithmetic mean. Okay, when we consider the arithmetic mean, it is 23. And when we are considering the geometrical mean, then the new relation is delta dash is equal to 30 into chi a minus chi b the whole square. Okay, so from this one, chi a minus chi b, the whole square is equal to 1 divided by 30 into delta dash, or chi a minus chi b is equal to root of 1 divided by 30 into root of delta dash. Okay, that is chi a minus chi b is equal to root of 1 divided by 30 is equal to 0.182 into root of delta dash. Okay, this is our new relation. Okay, so we have a new relation chi a minus chi b is equal to root of 182 0.182 into root of delta dash. Okay, and in calculations we'll be using this relation because this relation gives better results. Okay, so here also you have to remember that when you are calculating root delta dash, then you have to put your dissociation energies in kilocalorie per mole. Okay, for sometimes you may be given the values in kilojoules. For example, when a question is asked in the examination where you are given the bond dissociation energies in kilojoules per mole, then you have to convert that kilojoules per mole to kilocalorie per mole, right? So how can we convert kilojoules per mole to kilocalorie per mole? So 1 kilojoule, 1 kilojoule is equal to 0.239 kilocalories. So you can use this relation. Okay, so if it is given in kilojoules, then you have to multiply it with 0.239. Then it will be converted to kilocalorie. So that should be kept in mind always. Okay. So now you know about the Pauling's approach of electronegativity. So in these relations which was put forward by Pauling, we have electronegativity difference between two elements. So if the electronegativity of one of the elements is fixed, if the electronegativity of one of the elements is fixed, then we can calculate the electronegativity of all other elements, okay, from this data. Okay, for example, if you are taking one of the electronegativities as for example, if you are taking the electronegativity of hydrogen as 2.1, then you can use this relation to calculate the electronegativities of other elements. So Pauling calculated the electronegativities of many other elements based on the electronegativity of hydrogen, which was given as 2.1. Okay, so there is another approach. The fluorine's electronegativity is given. Okay, it is fixed as 4.0, and based on that also the electronegativities of other elements can be done. Okay, so either you can put hydrogen's electronegativity as 2.1 or fluorine's electronegativity as 4.0, and based on this one you can calculate the electronegativities of many other elements. Okay, so I hope you understood the electron Pauling's approach of electronegativity, and in order to check whether we understood fully, let us do one calculation. Okay, so there is a problem. The problem is that calculate the electronegativity of carbon. Calculate. Please write with me. When you are watching this lecture, please take a notebook with you and write all the things what you are watching here. Otherwise, you may not feel confident in the examination. Okay, so that should be a habit whenever you are watching my online lectures. So the problem is that calculate the electronegativity of carbon. Calculate the electronegativity of carbon. Electronegativity of carbon from the following data. From the following data. Okay, EHH means by E it is meant bond dissociation energy. EHH is equal to 104.2 kilocalorie per mole. Okay, ECC, that is the bond dissociation energy of carbon-carbon bond, that is equal to 83.1 kilocalorie per mole. Okay, and ECH is the bond dissociation energy of carbon hydrogen bond, that is 98.8 kilocalorie per mole. So all the bond dissociation energies are given in kilocalorie per mole, so you don't need to do any other unit conversion. Okay, so now we can directly apply our relation. So from our relation that we got based on the Pauling's approach, delta dash is equal to that is equal to ECH. because we learned that delta dash is equal to 0.182 into delta dash, root of delta dash. Here we have to get what is the expression for delta dash. It is given here. Delta dash is equal to EAB minus root of EAA into EBB. So the same relation we can put it there. Instead of A, we can give a carbon, and instead of B, we can give hydrogen. Okay. So instead of EAB, we have to write as ECH. That's all. Okay. So we can write here delta dash is equal to ECH, that is the bond dissociation energy of carbon hydrogen, minus, so we are going to take the geometrical mean, not the arithmetic mean. Okay, that is root of EHH into ECC, right? EHH into ECC. Okay, that is the delta dash. That is equal to, what is ECH? It is already given. ECH is equal to 98.8 minus root of EHH into ECC. EHH is equal to 10104, right? 104 into 104.2 into 83.1 into 83.1. Okay, so that is equal to 98.8 .8 minus root of 104.2 into 83.1. You can calculate it. The value will be 5.75 kilocalorie. Okay, kilocalorie per mole. Kilocalorie per mole. Okay. So this is the delta dash, and from this one we can use we can calculate chi c minus chi h. So chi c minus chi h means the electronegativity difference of carbon and hydrogen. Chi c minus chi h, that is equal to our relation is 0.182 into root of delta dash, right? So 0.182 root of delta dash, that is equal to 0.182 into root of 5.75, root of 5.75. Okay, that is equal to 0.185 into root of 5.75, that is equal to 0.44. Okay, so from this one, chi c is equal to 0.44 plus chi h, right? Chi h, and chi h is what is chi h? It is also given in the data, or we can use this one, 2.1. I have already said what is chi h. So chi h is equal to 2.1. Okay, so we can substitute 2.1 instead of chi h. So chi c is equal to 0.44 plus 0.44 plus 2.1. 0.44 plus 2.1, that is equal to 2.54. Okay, so that is the electronegativity of carbon. So electronegativity of carbon can be found in this way. Okay, we used Pauling's approach to find out the electronegativity of carbon. So chi c is equal to 2.54. Let me put that in a box. Okay, we will use this later on. Okay, 2.54. Now you know what is Pauling's approach of electronegativity and how we can get the electronegativity of different elements compared to the electronegativity of hydrogen or the electronegativity of fluorine. Okay, and now we can go for another approach of electronegativity. Okay, second approach of electronegativity, that is Allred and Rochow's approach. Allred and Rochow's approach. Allred and Rochow's approach. Allred-Rochow's approach. Okay, so in Allred and Rochow's approach, okay, the electronegativity is considered as the electrostatic force of attraction exerted by the nucleus of an atom on the valence electron. Okay, let me write it here. You can also write it down in your notebook. From this one approach, Allred and Rochow considered the electronegativity as the electrostatic force of attraction, of attraction, electrostatic force of attraction exerted by the nucleus, exerted by the nucleus of an atom, on the valence electrons, Okay, so this is the definition by Allred and Rochow. Electronegativity of an atom is the electrostatic force of attraction exerted by the nucleus of that atom on the valence electrons. Okay, and this approach make use of Z effective because it is talking about the electrostatic force of attraction or power of attraction or the force of attraction by the nucleus over the valence electrons. Means nucleus in the influence valence electrons അതായത് ആറ്റത്തിന്റെ പെരിഫറിയിൽ എത്രമാത്രം ഉണ്ട് എന്നാണ് ഈ അപ്രോച്ച് കണക്കാക്കുന്നത് അല്ലേ. ആറ്റത്തിന്റെ സെന്ററിൽ ഇരിക്കുന്ന ന്യൂക്ലിയസിന്റെ ഇൻഫ്ലുവൻസ് ആറ്റത്തിന്റെ സർഫസിൽ അല്ലെങ്കിൽ പെരിഫറിയിൽ എത്രമാത്രം ഉണ്ട് എന്നുള്ളതാണ് ഈ അപ്രോച്ച് കണക്കാക്കുന്നത്. അതുകൊണ്ട് തന്നെ then it is making use of the concept Z effective. Okay, Z effective, or you know that what is Z effective? That is the effective nuclear charge. It is called effective nuclear charge. Means the valence electron, ഒരു ആറ്റത്തിന്റെ ഏറ്റവും പുറത്തിരിക്കുന്ന ഇലക്ട്രോണിന് ന്യൂക്ലിയസിന്റെ ഫുള്ള് ചാർജും എക്സ്പീരിയൻസ് ചെയ്യാൻ പറ്റില്ല. കാരണം എന്താണ്, ആ വാലൻസ് ഇലക്ട്രോണിന് താഴെ ഒരുപാട് ഇലക്ട്രോൺസ് ഉണ്ട് അല്ലേ. അല്ലെങ്കിൽ ആറ്റത്തിന്റെ പെരിഫറി നമ്മൾ പരിശോധിക്കുകയാണെങ്കിൽ ആ പെരിഫറിക്ക് തൊട്ട് താഴെ മറ്റ് ഇലക്ട്രോണിന്റെ ഒരുപാട് ക്ലൗഡ് അവിടെ ഉണ്ട്, പ്രസന്റ് ആണ്. So because of this electron cloud below the periphery or the surface of the atom as a whole, there will be some screening of the nuclear attractive force before reaching the surface അല്ലെ. സർഫസിൽ എത്തിച്ചേരുന്നതിന് തടസ്സമായിട്ട് ന്യൂക്ലിയർ അട്രാക്റ്റീവ് ഫോഴ്സിന് ഒരു സ്ക്രീനിങ് അനുഭവിക്കേണ്ടതായിട്ട് വരും. അല്ലെങ്കിൽ ആറ്റത്തിന്റെ ഏറ്റവും പുറത്തിരിക്കുന്ന ഇലക്ട്രോണിന് ന്യൂക്ലിയസിൽ നിന്നുള്ള ഫോഴ്സ് ഓഫ് അട്രാക്ഷൻ ഫുള്ളായിട്ട് അനുഭവിക്കാൻ സാധിക്കില്ല ബിക്കോസ് ഓഫ് ദ സ്ക്രീനിങ് ബൈ ദ ഇന്നർ ഇലക്ട്രോൺ. സോ ദിസ് is called the effective nuclear charge, the charge experienced by the outer electron, okay, or nuclear charge experienced by the outermost electron. Okay, that is effective nuclear charge at the periphery of the atom. Okay, and this can be calculated by some methods. For example, we can calculate this by Slater's rule. Okay, I am not going to the details of this one, but at a certain stage you can learn this. Okay, so this can be obtained by Slater's rule. Okay, so this Allred and Rochow's approach make use of the effective nuclear charge in order to calculate the electronegativity of an atom. Okay, so there is a direct approach. So now the electronegativity of an atom chi is equal to 0.359 into Z effective divided by R square plus 0.744. Okay, this is the Allred and Rochow's equation for electronegativity. Chi is equal to 0.359 Z effective divided by R square plus 0.744, where R is the covalent radius of the atom. That is the covalent radius of the atom. And this is expressed in angstrom units. Okay, and the values that we can calculate from here. Okay, if you know the Z effective or effective nuclear charge and the covalent radius of the atom, then we can directly calculate the electronegativity of the atom, okay, directly without considering any other element, okay. So this is a direct approach to get the electronegativity, okay. So in order to understand this approach, let us do a problem, okay. The problem is calculate the electronegativity of carbon atom. Calculate the electronegativity of carbon atom. We are doing the same. Okay, here also we calculate the electronegativity of carbon atom, and now we are going to calculate the electronegativity of carbon atom in another approach. So the problem is that calculate the electronegativity of carbon atom using Allred-Rochow method. Using Allred-Rochow method. Also, some other data is given in the question. The covalent radius of carbon atom is the covalent radius of carbon atom is 0.77 angstrom, 0.77 angstrom, and the Z effective or effective nuclear charge Z effective is equal to Z effective is equal to Z effective is equal to 2.90, okay. So this is the question, and from this one we have to calculate the electronegativity of carbon atom. From another approach, we already calculated the electronegativity of the carbon atom, and from this approach also we are going to calculate the electronegativity of carbon atom. So here we are going to use the Allred-Rochow's equation for the electronegativity, and Allred-Rochow's equation is chi, or we are going to calculate the chi of the carbon atom or electronegativity of the carbon atom, that is equal to 0.359 into, okay, Z effective divided by R square, Z effective divided by R square plus 0.744, okay. That's what we are going to calculate. So let us substitute for the values of Z effective and R square in this equation. Then we get 0.359 into Z effective in this case is given as 2.90, right? 2.90 divided by R, or covalent radius of the carbon atom, is 0.77 angstrom. So we don't need to do any unit conversion here because it is already given in angstrom. If it is given in any other scale, you have to convert that to angstrom before doing this step. Okay, that's very important. So 0.77 square plus 0.744. Okay, so if you are calculating this, we get 2.50. Okay, so carbon atom's electronegativity chi is equal to 2.50 in this case. So when we calculated the electronegativity of the carbon atom by the second approach, we get the value 2.50. Now you can look what was the value we obtained using the first approach. Using the first approach, we got chi c is equal to 2.54. Here chi c is equal to 2.50. So we are getting close values, right? 2.50 and 2.50, they are closer, and it means that we get almost similar results, remarkably similar results in Allred-Rochow's approach and when compared to the Pauling's approach. Okay, and therefore now we are switching to the next method, that is next approach, that is Mülliken's approach. So the third method is Mülliken's approach. So we are switching to the next approach, Mülliken's approach, and this approach depends upon the average of the ionization energy and electron affinity. We have already learned the ionization energy and electron affinity. And if you know the ionization energy and electron affinity of an atom, and from these values we can calculate the electronegativity. Okay, ionization energy and electron affinity. Ionization energy and electron affinity. Okay, from these two we can calculate the electronegativity. So in this approach, we have an empirical relation again, that is electronegativity is equal to chi is equal to 0.374 into average of the ionization energy and electron affinity, that is IE ionization energy plus electron affinity EA divided by 2, okay, plus 0.17. Okay, so 0.374 into average of the ionization energy and electron affinity plus 0.17. That will give the electronegativity of the element. So in other words, we can write it like, we can take this divided by 2 to here, then we can write it like 0.187 into ionization energy plus electron affinity plus 0.17. Okay. Okay, and here we have to take care that here the ionization energy and electron affinity are given in electron volt. Okay, these things you have to consider. So if it is given in some other units, you have to convert to electron volt. Okay, so that is very important. So ionization energy and electron affinity are given in electron volt in this relation. Okay, so if you know the ionization energy and electron affinity of an element, of a particular element, then we can calculate the electronegativity of that element. Okay, so we can do a problem, and from this problem we can understand how we can get the electronegativity of an element from the ionization energy and electron affinity values. For example, let us take the case of carbon atom again. Okay, because we are considering the case of carbon atoms in two approaches already, so we are going to calculate, we are going to take the same in this approach also. We can compare then the values of electronegativity getting in different approaches. So the problem is that calculate the ionization energy, calculate the electronegativity. Okay, calculate the electronegativity of carbon atom, carbon atom by Mülliken's approach, given that ionization energy and electron affinities are 11.2594 electron volt and 1.262 electron volt respectively. Okay, so from this data we have to calculate the electronegativity. So electronegativity chi is equal to 0.187 into ionization energy plus electron affinity, okay, plus 0.17. That is the Mülliken's equation for electronegativity. That is equal to 0.187 into ionization energy is 11.259 plus 1.262 plus 0.17. So if you are doing this, then we can get a 0.187 into 12.521 plus 0.17. Okay, and that is equal to 2.3414 plus 0.17, and that is equal to 2.51. So chi c or electronegativity of the carbon atom in this approach is equal to 2.51. Now you can compare the electronegativities obtained in three different methods. Okay, in the first approach, means in Pauling's approach we got 2.54, and the Allred-Rochow's approach we got 2.50, and in Mülliken's approach we got 2.51. All these values are closer to each other, right? So we can get the electronegativities of elements in different approaches. Now I hope you already have an idea of the electronegativity, what is meant by electronegativity. So electronegativity is the tendency of the atom to attract the electrons towards its side. Okay, so in different approaches we can get a measure of the electronegativity, and the rest of the things we will discuss in the next class. Thank you for watching and stay tuned.